In this last lecture on thermal processing of metals, I want to cover a process called precipitation hardening. So all precipitation hardening is the creation of small uniformly dispersed second phase precipitates within a matrix phase, and these precipitates block dislocations, which means it increases strength. So what I'm showing you here is a micrograph of an aluminum alloy, and you can see that there are these dark particles. These are second phase particles that have precipitated out of the lighter colored matrix, and those particles will serve to like I say, block dislocations and enhance the strength of the metal. So what we want to talk about now is how do we achieve this sort of microstructure. Well, there's actually a two-step process. And we'll talk a little bit about this phase diagram and why we have to have this kind of phase diagram in the next slide. But the procedure is fairly straightforward. We first do what's called a solution heat treatment, and all that is we raise the temperature, so we have to be below this maximum solubility, so somewhere to the left of this point. We raise the temperature so that we're in the all solid solution region, in this case T naught. We hold there to get a complete solid solution, and then we quench. Okay, so the quench is going to actually lock in a alpha phase with a higher concentration of whatever the alloying element is than is desired, and we call that a supersaturated solid solution. So that's the first step. In the second step, we do what's called a precipitation heat treatment. And all this is we then heat that supersaturated solid solution up to some intermediate temperature here shown by T2, and we hold there for some time until those beta particles begin to precipitate out of the alpha matrix. Okay, so it's fairly simple. That's all the procedure requires. But let me tell you a little bit about what's required of the metal itself in terms of the phase diagram in order to be able to even do this heat treatment, and why we didn't talk about it with respect to sort of our plain carbon steels. The first thing is that we have to have some appreciable maximum solubility limit. So remember, this is your maximum solubility limit, and we need it to be at least several weight percent of whatever alloying element we have. The reason is if we don't have that, then we don't have enough material to even to make enough particulates of any size or consequence to be significant. Otherwise, we'll just have a sort of a solid solution strengthening um, metal. So requirement one is that we have to have some maximum solubility. Obviously, in order for this to work, we have to have a line that we can cross when we raise the temperature up, and then when we hold it at this intermediate temperature. If we don't cross a solubility line, no precipitates are going to form, and so we require there to be a rapidly decreasing solubility limit with concentration. So remember, with our eutectoid transformation, at least in steels, our eutectoid composition was something like 0.76 weight percent carbon, which is obviously not at least several weight percent, so it doesn't work there. Okay, a couple other features to be aware of. The particulates that we form are going to grow larger with time just to minimize their surface to area to volume. Just like we've talked about other particles like the forming of spheroidite or things like that. But there's a little bit more to consider. If the particles are too small, then they don't block dislocations effectively. On the other hand, if the particles are too large, then they don't block dislocations effectively either, because you just have a bunch of large particles and the space in between them, the dislocations can move freely. And what that implies is that there's a sweet spot. And so that's what this graph is showing you. This is precipitation heat treat time versus the tensile strength of your part, and you can see that early on we increase the strength as the precipitates form, and there's lots of small precipitates. We call that aged. But as we continue to proceed along that process, then the strength actually decreases as the particulates grow, and we refer to that state as being overaged. So the upshot here is that if you increase the temperature, um, uh, well, the increasing the temperature obviously increases the aging, and the other thing is that you can't use any sort of precipitation hardened alloys at elevated temperature because it causes this overaged state. So with that pretty much sums up what you need to know about precipitation hardening, at least for the purposes of this class.